All right, in this video, we're going to take a look at a stoichiometry topic for grade 11 chemistry, calculating things with percent yields. When you create products in a chemical reaction, we say that you are yielding product. So if you've calculated with a stoichiometry set of unit multipliers the amount of product that you should form, maybe you've answered a stoichiometry question, what you found when you calculated the amount of product that you expect to get is called the theoretical yield. So that's basically just the answer to a stoichiometry question if you're calculating how much product you should form. When you go to the lab and actually do the experiment, then you're going to get that product. You're going to isolate it. Perhaps you filter it or you collect it somehow. What you actually collect in the experiment in the lab is referred to as your actual yield. And for a variety of reasons, those things are not normally the same. You expect to get a certain number of cookies when you bake cookies, if you follow the recipe, but when you actually finish baking, the number of cookies you have is probably a little different from what you expected. So your actual yield is different from the theoretical yield. To get the percent yield, you just take the actual yield, divide by the theoretical, and multiply by 100. So let's do a simple calculation with percent yield. The simplest type is simply to find the percent yield. So here we have a question, 2.23 grams of potassium chlorate is heated. The oxygen gas that is produced is collected, and a student collected 512 milliliters of oxygen measured at STP. What is the percent yield? You could start by thinking about what type of reaction this would be, and then writing a balanced chemical equation. The potassium chlorate, KClO3, is being heated, and it sounds like it's basically just decomposing. It's going to be a decomposition reaction. It's going to decompose, and we know one of the products is oxygen gas, so the other product here will be potassium chloride. That would have been a little bit hard to predict. If you're beginning as a chemistry student, you can be forgiven if you weren't able to perfectly predict those products. But now that we have the equation, go ahead and balance it. Since there's 3 O's on the left and 2 O's on the right, the lowest common multiple would be 6. So I'm going to put a coefficient of 2 in front of the KClO3 and a coefficient of 3 in front of the oxygen. And then because we have 2 KClO3s, we'll get 2 potassium chlorides as among the products. So there's our balanced equation. To do a stoichiometry problem, you have to have a balanced equation. So this student heated 2.23 grams of the potassium chlorate. Why don't we calculate the volume of oxygen gas that should have been created, measured at STP? I'm going to find the volume because we were given the actual volume that the student collected, so we'll calculate the theoretical volume that should have been collected. So to do that, we'll use some unit multipliers. 2.23 grams of potassium chlorate. Pause the video and see if you can set up your own string of unit multipliers to find the milliliters of oxygen gas produced. So the first thing I'll do is switch the grams to moles of potassium chlorate. Then using the balanced equation ratio, we can switch moles of potassium chlorate into moles of oxygen. Now, because the gas was measured at STP, standard temperature and pressure, we can do something else. It's a gas, so at STP, we can switch moles of gas, in this case oxygen, into liters of gas, because we know that there's 22.4 liters for every mole of gas measured at STP. And then finally, because the question told us the number of milliliters of gas, let's switch the liters to milliliters and we'll have our theoretical yield of oxygen. Go ahead, put numbers in, and get the answer to the question. So the first thing we need is a molar mass. So the molar mass of potassium, 39.1, chlorine, 35.45, and 3 oxygens. That guy's molar mass, potassium chlorate, is 122.55 grams. And then from the balanced equation coefficients, we can see that 3 moles of oxygen are produced when 2 moles of potassium chlorate decompose. We mentioned earlier that at STP, a mole of any gas, in this case oxygen gas, has a volume of 22.4 liters. And then a recipe everybody should know that there's 1,000 milliliters in a liter. So according to our unit multipliers, let's do the calculation on our calculator. The theoretical yield of the oxygen should have been 611 milliliters produced. So this is what our stoichiometry calculation predicts. This is our theoretical yield. Okay, if you could do this experiment perfectly with no sources of error, that's the maximum amount of oxygen that you should get. But in fact, when this person did the experiment, they got a little less than that. They collected 512 milliliters of oxygen gas. So that could be that they lost some gas. Maybe they were collecting by water displacement and some gas escaped. Maybe some of the gas dissolved in the water if they were collecting it by water displacement. There's a variety of reasons why you won't get what you thought you should get. Many of those reasons are sources of error in the experiment. So now we can calculate the percent yield. According to our formula, we take the actual yield and we divide by the theoretical yield and we multiply by 100. So this is just logic. If you actually made 512 milliliters, but you thought you should get 611 milliliters, so you're short by about 100 milliliters, then your percent yield is going to be 83.8%. So when this person does the experiment, instead of getting 100% of the oxygen, they're only getting about 84%. All right, so that's the simplest type of percent yield calculation, where you just are told the actual yield and you calculate by stoichiometry the theoretical yield and then just plug things into your formula to get the percent. But you can also use percent yield in a slightly more difficult calculation. It's really not more difficult, but perhaps more confusing for some students. So given the percent yield in the experiment, so if this person were to repeat the experiment, and let's assume they would make similar errors and things, so they're going to get about 83.8% of oxygen that they would otherwise have made. What mass of potassium chlorate should they use if they need to produce 50 grams of oxygen gas? So they need to make 50 grams of oxygen. They have to have that at the end, but they're only going to make 83.8% of what they aim to make, right? The percent yield is only 83.8%. There's more than one way to do this question, but let me start with this. If you need to make 50 grams of oxygen, so 50.0 grams, that's what you have to make. This is like our actual yield, right, that we need to get. The question becomes, what should we aim to make? If I aim to make 50 grams, well, I'm not going to actually make that, right? I'm only going to make 83.8% of that. So what should I aim to make? Well, if I take the 50 grams and plug that into my percent yield calculation, but I'm going to make this the theoretical yield. So I'm going to assume that this is the amount that I have to get. So what I'm going to calculate is what amount, or what should the theoretical yield be to aim for. So 83.8% would be the actual yield that I must make, 50 grams, divided by some amount that I should aim to make theoretically, times 100, right? So when you look at what I'm doing here, I'm just taking the percent yield that we had already found, plugging it back into the percent yield formula, but I'm taking the 50 grams, which is what I have to make, I'm putting that in as my actual yield, and I'm going to calculate what yield should I aim to create. So solving for this, x is going to be, let's see, 50 divided by, just rearranging my formula, 50 divided by 83.8 times 100. So 50 divided by 83.8 times 100. So I should aim to make 59.7 grams of oxygen. This is what my theoretical yield should be. Okay? Think about that. If I aim to make close to 60 grams of oxygen, and I'm only going to get about 84% of what I aim for, then it makes sense. I'll end up getting 50 grams, which is what I'm told I have to make. So now that I know the theoretical yield that I should aim for, I'm going to take that as my starting point and set up some unit multipliers to answer the question, what mass of potassium chlorate would give me this theoretical yield? So let's switch our grams of oxygen to moles of oxygen. Then we'll use the balanced equation, switching moles of oxygen to moles of potassium chlorate, and then using its molar mass again, switch the moles of potassium chlorate to grams of potassium chlorate, and I'll have my answer. So the molar mass of oxygen, 32.00, there's O2, and then again from my balanced equation up above, 3 moles of oxygen for every 2 moles of potassium chlorate, and then the molar mass of potassium chlorate from up above, 122.55. Grabbing a calculator, 59.7 divided by 32 times 2/3, and then multiplied by 122.55. I'll keep 3 significant digits, so 152 grams of potassium chlorate should be used. All right, so this was a little bit of a harder percent yield question because we weren't just calculating the percent yield, we were using it to solve another question. So because we were going to get less than what we aim for, we're only going to get 84% of what we aim for, we started by taking what we wanted to make, 50 grams, and we calculated what mass of oxygen we should aim for. So the 50 grams is 83.8% of the amount that I'm aiming for, the 59.7 grams. Then we took the amount that we should aim for as the starting point in our stoichiometry calculation, and we calculated that you should use 152 grams of the KClO3. All right, so percent yield, the actual amount of product you get, divided by what you thought you should get, your theoretical yield, which is the answer to a stoichiometry problem, and to get a percent, you multiply by 100.